So now that we've got somewhat acquainted with what power series are and to try and be able to tell when a power series is convergent or when a power series is divergent, or as we saw in the previous section, we found the intervals containing all the values of x for which that power series converges. Now we can think of power series themselves as functions. And so we want to think about what kind of functions we can represent as power series. And here's a familiar one that we've seen a few times, which is the power series representation of the function 1 over 1 minus x. And if we remember, this is the power series 1 plus x squared plus x cubed, and so on, where here we think of it as the geometric series x to the n. We know that this will converge for x that are less than 1 in absolute value. Otherwise, it will diverge. So what we have is a way of representing the function values of this function 1 over 1 minus x as the sum of this infinite series here. So as we've seen before, right, we can look at the absolute value of x here as giving us the radius of convergence equal to 1. And if I were to open this interval, we see that the interval of convergence is just the open interval negative 1 to 1. Notice that at the endpoints it will diverge. So at -1 and at +1 it will diverge. So our interval of convergence is this open interval. Now we want to look at different functions that can be formed as a power series by manipulating this function through substitution. For instance, I could substitute in different values of x here, or different expressions for x, and that would give me different versions of a power series. Or we can multiply this function by power functions of the form x to the n, and that will give us variations of this power series as well. And we'll see later on that we can also manipulate this through derivatives or integrals to form other power series as well. But let's take a simple example. Let's express the function 1 over 1 plus x squared as the sum of a power series and find the interval of convergence. So in this case, looking at the function 1 over 1 plus x squared, we can relate this to the function 1 over 1 minus x by replacing x with negative x squared. So you see, in this case, we can come back to our representation where here we're just taking this value of x that was in our power series of x to the n and replacing that with negative x squared, right? So if we do that here, we get the power series negative x squared to the n, which in this case is just substituting in negative x squared for x into this power series here. And then I can manipulate this a little bit. Negative 1 to the n times x squared to the n, which is x to the 2n. So really we can see that this is just taking the series 1 plus x squared, 1 plus x squared, and so on, and replacing x with negative x squared. And in this case we get the alternating series, one minus x squared plus x to the 4th minus x to the 6th plus x to the 8th, and so on. Now, one thing to keep in mind was that the representation that we had here, here I should say here, whatever we put in for x, right here I'm calling it star, whatever, could be anything there. whatever is in the parentheses here that we're putting into this power series will converge only when it's less than 1 in absolute value. So in this case, what we did was we substituted negative x squared into the power series. So we know this converges when the absolute value of negative x squared is less than 1. Of course, taking the absolute value of negative x squared is the same as the absolute value of positive x squared. And here, taking the square root of both sides, we get just the absolute value of x is less than 1. So we see it's the same radius of convergence as before, and the interval of convergence will be from -1 to 1. And in this case, we can also note that at the endpoints, you can check here, if I substitute x equals 1 into this power series, you get a divergent series. And if I substitute x equals -1 into the power series, you get another divergent series. So our interval of convergence here is the open interval from -1 to 1. Now let's look at the function 1 over x plus 2. Again, here our goal will be to try and manipulate it to get it into this form, 1 over 1 minus something. So we can use the power series that we have for that function. And in this case, what I'll do is we know we need our constant term to be a 1. So what I'll do is I'll first factor out a 1/2. And then this becomes 1 plus x over 2. Okay, so just switching the order of the terms, factoring out a 2 from those two terms in the denominator. And then notice it also needs to be a minus there. So the next thing I'll do is I'll write it as 1 over 1 minus negative x over 2. Okay. So we see it's now in this form, 1 over 1 minus something. And in this case, that something is negative x over 2. So I'm going to put that into our power series here for x. So it'll be 1/2 sum of negative x over 2 to the n. And again, to simplify this a little bit, I could write this as -1 to the n, x to the n over 2 to the n. And then I noticed that here, 1/2 multiplied by the terms of the series will multiply the factor of 2 to the n here in the bottom by 2. So if you want to imagine this, what the series is, it's just doing 1 minus x over 2 plus x squared over 2 squared minus x cubed over 2 cubed, and so on, right? Right, see it's alternating, and then the power of x over 2 goes up with every term. So if I'm multiplying each term by 1/2, right, then we're going to increase the power of 2 by 1. So it'll be 1/2 minus x over 2 squared plus x squared over 2 cubed minus x cubed over 2 to the 4th, and so on. So you see we just increased the power of 2 by 1. So we can write it as the series of -1 to the n, x to the n, over 2 to the n plus 1. Now to see the radius of convergence here, we know that this converges for, again, we know that whatever we're putting in for x in this series here converges when it's less than 1 in absolute value. So same idea here, it converges when the value that we put in for x is negative x over 2, so the absolute value of negative x over 2 is less than 1. Which means that here the absolute value of x over 2 is less than 1. And that means that the absolute value of x is less than 2. So here you see the interval, or the radius of convergence is 2. And our interval of convergence would be from negative 2 to positive 2. Again, we can just quickly verify mentally here that when I substitute x equals negative 2, or when I substitute x equals positive 2 into the series, you get a divergent series. Because here, for instance, if I substitute in negative 2, you get 2 to the n over 2 to the n minus 1 simplifies to 1/2, and so you have a series with just the constant term 1/2. If I substitute positive 2, then you get a series negative 1 over 2, negative 1 to the n over 2. And again, that's just a constant series, but alternating between negative 1/2, positive 1/2. In either case, it's a divergent series. So here our interval of convergence does not contain the endpoints. In this next example, we're going to build on the power series that we just created by including a factor of x cubed in the numerator. Okay? So notice this is the same denominator. We have the power series that we created in the previous example, but now we're multiplying it by x cubed. So we can think of it as we're taking the power series that we created previously and multiplying the whole thing by x cubed. And here I'm just going to borrow the work that we did in the previous slide when we created the power series of 1 over x plus 2. So again, you can look at the details there to see how we created that power series. So is the power series negative 1 to the n, x to the n over 2 to the n plus 1. And now, again, we can think of this as like I'm just multiplying x cubed to each term of the series. And when I distribute it into each term of the series, what you notice is that it's just going to increase the power on each term by 3. So you're adding 3 to the power. So what we would have here is the same series, but adding 3 to the power of x. So you can imagine here that now the first term is x cubed over 2. The next term would be x to the 4th over 2 squared. The next term would be x to the 5th over 2 cubed, and so on. X to the 6th over 2 to the 4th. So really what I can just do in the form that we have it here is I can just write x to the 3 times x to the n as x to the n plus 3. So it's negative 1 to the n, x to the n plus 3 over 2 to the n plus 1. So notice that this operation that we did here didn't change the radius or interval of convergence. In other words, the same radius and interval of convergence that we had before is the same here. So it still only converges when x is between negative 2 and positive 2.